This is going to be in your calculator. Using the calculator that you're going to use on the test is really important because you got to know where these keys are, and you can't use your phone on the test. So I would not suggest using your phone during class for your calculator. Use your calculator or use my calculator so that on test day, you know what you're doing with the calculator, okay? All right. So exponentials. The first part's just a review. If m is a positive integer, then x to the m is equal to x times x times x times xm times, right? It means repeated multiplication. So if I have 3 to the 4th power, that means 3 times itself 4 times. If I have negative 3 to the 4th, now here's what we've talked about with calculators. The negative is not connected to that exponent. So that's equal to negative 1 times 3 times 3 times 3 times 3. Whereas if I have negative 3 to the 4th, the negative and the 3 are both being taken to the 4th power. So that's equal to negative 3 times negative 3 times negative 3 times negative 3. This differentiation is so important, and one of the things that students mess up on and get the wrong answer from with their calculator all the time. Pay attention to what is being taken to the exponent. Is the negative being taken to the exponent or just the number? Okay? So here, this would be negative 81. And this would be positive 81. Does that make sense to everybody, the difference between those things? Okay? All right. The base cannot be 0. Okay? But when the exponent is 0, the answer is always 1. Again, another mistake students make. They like to say that anything to the 0 power is 0. It's 1. Okay. So no matter what it is, 4 to the 0 equals 1. Negative 3 to the 0 equals 1. 0 to the 0 is undefined. Okay. Over to the right from there, that little arrow that's after that one that goes to the right. If m is not equal to 0. How did I do that? I think that's supposed to be less than 0. Let's change that. If m is less than 0. Okay, that means that your exponent is a negative number. So if we have x to the negative m, what a negative in the exponent tells us is, hey, I'm in the wrong place. If I'm a negative exponent in the denominator, move me to the numerator. If I'm a negative exponent in the numerator, move me to the denominator. So if I have x to the negative m, that's 1 over x to the positive m. If I have 2 to the negative 3, that says, hey, I'm in the numerator, you're in the wrong place. Move it to the denominator. 2 to the 3rd power. Okay, which would be 1 over 8. If I have negative 2 to the negative 3rd power, remember this negative out in front is not in the wrong place because it's not in parentheses. That exponent does not own that negative out in front. So the negative is just fine. Negative 1 over 2 to the 3rd place, to the 3rd power, excuse me. Does that make sense to everybody? Is all this familiar? Does it feel like a review for everybody? Yeah. Okay.
That and then that's greater than
Less than.
m is greater
Less than 0. So it's a negative number. If your exponent is negative.
That's the same as m is not equal to 0.
No, yes, that's what it should say, less than. So this is, M is negative. Are we good? Can I erase this side of the board? Y'all wanna talk to me today? I like y'all talking to me. Y'all usually are good at that. Okay. Right. When we have the same base, but our exponents are different, okay? So we're multiplying. So here my bases are the same. I've got multiplication in the between. My exponents are different. They can be the same. The rule is that we add the exponents equals to x, a plus b. Let's look at why that happens. Let's say I have 2 to the third times 2 to the fourth. Okay, so what that means is 2 times 2 times 2 times 2 times 2 times 2 times 2. Well, how many 2's do I have there that I'm multiplying? 7. Okay, so it just ends up adding the exponents. Division, x to the a over x to the b, turns into subtraction. It's equal to x to the a minus b. Again, let's look at why that happens. I have 2 as a b, 2 to the fourth divided by 2 to the third. So that means I have 4 2's in the numerator and 3 2's in the denominator. And we can reduce these 2's. I'm left with 1 2 in the numerator.
Can you use for those two?
You could, yes. I was just trying to show the subtraction. Yeah. So 2 to the 4 minus 3. Be careful though, because sometimes you'll get a negative number. So if I had 2 cubed over 2 to the fourth, always remember it's the numerator exponent minus the denominator exponent. So that's equal to 2 to the third minus 4, which is 2 to the negative 1, which means, hey, that 2 is in the wrong place. That's 1 over 2. So when you start reducing 2 times 2 times 2 over 2 times 2 times 2 times 2, and we reduce, if everything in the numerator reduces out, you have to have a 1 placeholder because there's always you can always multiply by a 1 and it doesn't change anything. So don't just think that the numerator just goes away. Like sometimes we think, oh, well, the denominator went away. But isn't there still a 1 in the denominator? Yeah, there's always a 1 in the denominator. We just don't write it all the time. Same thing happens if everything goes away in the numerator. We have to have that 1 to hold the numerator's place. Good?
So what's the difference? Oh, yes, you know. The 230 is over the 24 now, so the 240 is over the 230. Is that how we get that?
Yes, this one. This all goes together versus this all goes together. Now, a lot of times where students get confused. Good? Okay. A lot of times where students get confused with this is, let's say we have 2 to the fourth times 3 to the third. And students want to multiply this 2 and the 3 and get a 6 and then maybe add the exponents. You can't do that. When the bases are different, you can't combine it. You could do the math. You could say, well, 2 to the fourth is 16 times 3 to the third is 27, and then do the math. But we can't simplify it like we can when the bases are the same. Does that make sense? I'm going to come over here and erase this board then. Okay, and then we have power to a power. Now, when we start doing logarithms, we're gonna come back and talk about this power to a power rule a lot. Okay, so the power to the power rule says if I have some variable with a base to an exponent and I'm taking it to a power, we multiply the exponents. So x to the a times b. So let's look at why that happens. If I have 3 cubed all squared, right? That's going to be, according to this rule, 3 to the 6. So why does that happen? That says I have 3 cubed, which is 3 times 3 times 3, multiplied times itself. So times another 3 cubed, which gives me 6 of them. Okay? All right, and then the last one are fractional exponents. So if I have a base of x to the 1 over m, when you have this, the numerator is your exponent. The denominator is a root. So that means some type of radical sign. So that means the m root of x to the first power. So 4 to the 1/2 would equal the square root of 4. Remember, if you don't see a number on that radical, it means the square root. We don't have to write a 2. Okay, which would just be 2. Now I didn't divide by 2, I took the square root of 4. Okay, 27 to the 1/3 means the cube root of 27, which is 3.
So you put square root of 27 versus divided by 2.
I put, if you don't know what the cube root of 27 is, I put it in my calculator. Yeah, calculator's fair game. And you can use fraction exponents on your calculator too. There is such a thing as that. Okay. You're just going to use that fraction button. And so if I have x cubed to the 1/3, what, Chloe? What do you want? I wasn't calling you out on that to answer your question.
No, I was just remember.
Okay, all right. We multiply our exponents, so that's 3 times 1/3, so that's just x, the cube root. They're inverses of each other. I've got a cube, I've got a cube root. They inverse and give me 1. Okay, does everybody feel comfortable with those rules? Because we're going to apply all those rules with exponential functions and with logarithmic functions. And logarithmic functions, students always hate that word. It's just the inverse of exponents. Okay, it's just opposite. Logarithms are kind of confusing because mathematicians back way back in where made up this logarithmic rules. Okay, because they were doing these big calculations with astronomy and stuff, and they're like, well, this is multiplication. It would be easier if we could make this problem an addition problem. And so they made everything exponents because the math of exponents is always one step left. If we've got multiplication, it becomes addition. If we've got, where did I do it? A power to a power exponents, we turned it into multiplication. So it was a way for them to simplify math. They just made all the numbers exponents, and that's what logarithms are. Okay. But we got a little bit. We got to get through exponential functions before we get to logarithmic functions. All right. An exponential function has the form of a times b to the x. Okay. This a is never going to equal 0. It could equal 1. Okay. And b, this number, is always going to be greater than 0. It's always going to be a positive b. And it's not going to equal 1. okay? Because if it's 1, it's just a number. 1 to any power is 1, and then that would just be a constant of a. Does that make sense? All right, so some things that it would look like, you can see the examples on your paper, 2 to the x, 5 times 4 to the x. So 2 to the x, it's not the b that's 1, it's the a that's 1, right? The b is 2. In the next example, 5 times 4 to the x, the a is 5, the b is 4. Remember, please excuse my dear Aunt Sally, we have to do exponents before multiplication, so don't multiply that 5 times 4 and say that's 20 to the x. Okay, and then negative 2 times 1/2 to the x. So we have a 2, negative 2 here, and we have a 1/2 to the x here. So that's going to be multiplying a 1/2 times 1/2. We could change that 1/2 to 2 to the negative 1, and then we have a b that is not, it's still not going to be greater than 0. So it's going to be a decreasing exponential versus an increasing exponential. Okay. All right. So how do we graph these? What do exponential functions? Have y'all learned about, any of y'all take finance classes? Yeah. Okay. Exponential functions. Where do we see exponential functions? No? Investments in your money, right? We want to see that growth of your money shoot up. They tell you start saving as young as you can. Start putting that money and investing that money away as young as you're able to, because the growth of money is an exponential growth. So it starts off slow, and then hopefully by the time you get to my age, it starts shooting up and is making, your money is making money. That's exponential growth. That's where we see it the most. Okay, so it's this graph of something that starts off kind of slow and then eventually grows very hot. Okay, so we're no longer dealing with linear functions. All right, so y equals 3 to the x. And how we want to graph this is to make an XY chart. Okay, so -2, -1, 0, 1, and 2. We're going to substitute those x values. I tend to pick these values because what happens is if I pick x's that are way on out here, up here, they're going to be way off the graph because they're going to grow really fast. It's a graph that looks like this. So if you get way too far out here on the x, it's going to be too big of a number to fit on your normal graph. So these are the values I usually pick for it. Okay, so we've got 3 to the -2. We have 3 to the -1. We have 0 to the -1. We have 1. What did I do?
3 to 0.
Yes, thank you. I just got going. 3 to the 0, 3 to the 1, 3 squared. Okay. Now you can use your calculator to get these answers if you want to. Or we could say this is 1/3 squared, which is 1/9. This is 1/3, which is 1/3. 3 to the 0, anything to the 0 power is 1. 3 squared, or 3 to the first power is just 3, and 3 squared is 9. Okay, if you're using your calculator, make sure you know where those buttons are. I'm going to give you a second to see if you can put 1 or 2 of those into the calculator and make sure you get those answers. Anybody need me? Maybe. You got it? You go to math. So if you go to math and then scooch all the way over with your right, it'll give you the fraction. Okay. Yeah. Anybody else? Everybody got it? Good. All right, so let's look at what this graph looks like. These are my x values, these are my y values, so I'm graphing combinations of those graphs. Okay, so I go over -2 and up 1/9. That's just a teeny tiny bit. I go over -1 and up 1/3, over 0, up 1, over 1, up 3, and over 2, up 9. Okay, now, is there any number that I could put for that exponent? So I want you to think about this. If the exponent is negative, it gives us a fraction. If the exponent is positive, it's going to be a big number. Is there any number that's ever going to give me a 0? There's nothing I can put in that exponent that's ever going to give me a 0. Is there anything, if there's not an A out in front, if the leading coefficient or this number that's right here is 1, is there any way I'm going to get a negative number? No, because a negative gives me a fraction. There's nothing that's going to give me a negative. So when we graph this, it's got an asymptote at 0. An asymptote is a value that a graph gets closer and closer to. We do eventually learn that graphs can cross horizontal asymptotes. They never cross vertical asymptotes, but so it's going to get closer and closer to this x-axis without touching it. And then it's going to grow up and it's going to continue to grow. And we've got arrows at both ends. Okay. Now, we could shift it down by adding or subtracting something. We could make it negative if we put an A value that's negative in front. But for the parent function of an exponential, it will have an asymptote at 0 and the other side will grow. So it'll either look like this or this. Okay? All right. Now, let's look at what a fraction does to a graph. I'll do it over here. To the x, y equals. And x, 1/2 to the x, y. So we'll do those -2, -1, 0, 1, and 2. Okay, so we've got 1/2 to the -2, -1. No. Sorry. 1/2 to the -1, 0. 1/2 to the 0, 1/2 to the 1, 2 to the 1. Okay. Let me try that in your calculator, see what you get. Oh, Lord, I'm not used to plugging them like this. Sorry. 1/2 to the 2. Try that one. Because that's one that'll give you. If it doesn't. Right, let's do this one. Now do math. Number. Very good. All right, so I got for my answers 4, 2, 1, 1/2, 1/4. Yes? Okay, and we're gonna graph those. So over -2, up 4. Over -1, up 2. Over 0, up 1. Over 1, 1/2. Over 2, 1/4. It flipped our graph across the y-axis. It reflected it across the y-axis. So it just flipped it going the other way when you have a flat tube. Okay? All right. The number E is the next thing that we're going to work with. Because E is called Euler's number. It is sort of like pi. It is an irrational number, but it becomes very important when we do exponentials and logarithms because it becomes the base of a natural logarithm. And there was this mathematician whose name was Euler, and he named it after himself, the number E, which is 2.718, and there's another song that goes with this one to help you remember it, okay? So E, and it keeps going. E is an irrational number, meaning it's a decimal that never repeats and never ends. Its value is approximate. And when we change it to a decimal, we use 2.718. Now, your calculator has an E button. If you find the LN button, it usually shares the LN button. So there is an E button there that you can use. Okay? If anybody is in biology or in economics, E to the X is used a lot in biology and economics. Okay, it is a forensics. It's talking about growth and how fast something decays. We use E to the X. How fast a body cools to room temperature. You use it to approximate when a body. That's how they figure out when a body died. How many hours has passed since the body's died. So it's an important number. It came up a lot when they were using the study of logarithms, and it is considered a natural base to logarithms. Okay, so when we sketch graphs, there's going to be a general shape that we get. Okay, so if we have X and Y equals AB to the X. When X is 0, these ones that we just did with 0, we always got 1. The parent function always goes to the point 0, 1. But if A is not 1, the answer will be whatever A is. That A shifts that graph up or down depending on what the A value is. So the y-intercept is always going to be A. As long as we don't have anything added or subtracted here. Okay, when it's just in that form. When X is 1, the answer is going to be A times B. Because B to the first power is just B. So it would just be A times B. And that will give you 2 quick points on the graph. Okay? So the shape of the graph. When A is greater than 0 and B is greater than 1. Okay? So this could be a 1, 2, 3, whatever we want, any number here, greater than 1. And this number, or greater than 0, positive number here, and a number greater than 1 here. That's going to be that first shape we had. The next one that we did had an A that was greater than 0, but it had a B that was a fraction. So it was greater than 0, but less than 1. So a positive fraction. Less than 1. Okay, not an improper fraction, right? Because that would be greater than 1. So something like 1/2, 1/3, 2/3. Okay. The shape flips. It grows, or actually it decays. It gets smaller and smaller in that. Now, when this A value out here is negative, so this one right here reflected over the y-axis, right? We went from this way to this way. If we have an A that is less than 0 and a B that is greater than 1, it's going to take this graph right here and reflect it over the x-axis. So it's going to look something like that. And then if we combine that A less than 0 and B to become a fraction that's positive, so B is greater than 0 and less than 1, it's going to take that graph and reflect it over the y-axis, the general shape of that. So we get 4 general shapes. We have a growth, we have a decay, and then we have reflections of those over the x-axis. Okay, and it's that leading coefficient right here being negative that makes it come under the x-axis. So under the x-axis, above x-axis. As long as we don't have anything being added or subtracted to it, because then that's going to shift our graph again. Okay. Good so far? All right. So the amount of radioactive substance in grams after T days is given by the formula Q is equal to 10 times 1/2 to the 0.53 T. What is the initial amount of material? Okay, so that's when T is equal to 0. Initial amount, T equals 0. Well, what did we say? When T is 0, what's the answer always going to be? A, and what is A in this case? 10. Did you multiply the 10 times the 1/2? Is that what you did? Yes. Okay. So the initial value, you could substitute 0 in there in your calculator if you wanted to. Anything times 0 is 0, so that's 10 times 1/2 to the 0, which is 10 times 1, which is 10. Or you could just say the initial amount is A, which is 10. You can do the math, or you can use the little value that tells you the initial value is going to be A. Okay. How much material is left after 3 days? Okay, they said T was in days. Be careful, sometimes I think the WebAssign likes to trick you and change that to hours, and then you have to go back and figure out how many days that is. Just make sure that you're matching. This said T was in days, and this gave us days. So we just substitute 3 in for T. So 10 times 1/2 to the 0.53 times 3. Use your calculator. A 3. And if you've got that one down, go ahead and try the 8 days. Same thing, we're just substituting 8 in for T. Does anybody need me?
Shoot, sorry, that's not. I thought it was different.
All right, I got 3.3217, and for 10, was it 10 the next one? No, 8, 10 times 1/2, 0.53 times 8. I got 0.5292. As my X is increasing, what's happening to my output? It's decreasing, right? My leading coefficient is greater than 0. My B value is a fraction less than 1. So we have a graph that looks like this right here if we were to graph it. Okay, any questions? All right, turn the page and partner up with someone in the class. And I want you to try those next 3 questions with someone. I'm going to put the answers on the board so you can check them, okay? But go ahead, pair up, chit chat, make sure everybody knows how to do it. Be responsible for your friend next to you too, and Emily. And let me answer questions as we go to see if we can get this figured out, okay? Group work means you're chit chatting. Even if it's about how great your weekend is and your work. This is kind of a fun time. Relax. You make a mistake on the board, so just check my answers, your answers, please. Make sure I'm doing it right.
Yeah.
Notice how these word problems, I'm labeling my answers with the units. Make sure you do that, okay? You might want to show the values plugged in when you're doing your work so that if you do something wrong, I can give you partial credit on things. Showing me what you did allows me to know that you. It's not what it is, yeah. Showing it, so you can do that.
I showed you the days. I didn't do it for the rest of it.
Yeah, if you do that, then I can give you partial credit, because you're likely to hit the button wrong on the calculator, but know exactly how to do this, and then I can give you credit. Okay.
Oh.
It did not look like a rocket ship, I will say.
But you have like. I have a.
Make sure you shut that. It's like, I think partial credit from page one. No, she.
Yeah.
Especially in you know, choose to go back through your work that's what it is. All those offsets along with the rest, good line, but. It's out.
That's not what I'm doing, but down there, there's not one thing, I can go for it. I don't have to do it.
So your homework on this part won't be due till Friday, but it is open, so if you have time before Friday, go ahead and do it, okay?
That's internet. Oh, wait, I see. But, so do we always do zero on the first one of the location?
If it says initial value, yes, that's what X is, zero. All right, and if you've got them all, feel comfortable with it, you may pack up and turn my calculators in.